Good afternoon, I'm Hugh Dyer, the Director in RSK's Geosciences business. Welcome to the March edition of our 2025 series of Down to Earth webinars. These will cover a broad range of subjects and are available afterwards on our YouTube channel alongside previous talks. Our talk today will be given by John Finley and Anna Hitchmo from our Carbon Zero consulting team, providing a guide on decarbonisation through ground source energy. First, a brief note on housekeeping during the talk. All attendees' microphones are automatically muted through the webinar. During the presentation, you can post questions online and there'll be a Q&A session at the end of the presentation. We'll answer as many questions as possible at the end of the talk. Those that can't be answered due to time constraints will be answered after the webinar. Shortly after the webinar, you'll receive a link to a short survey. If you can take a few minutes to provide feedback so we can improve on our future webinars. Now, please let me introduce our speakers today. John has over 40 years experience of international engineering projects ranging from oil exploration and water resource management to renewable energy design and installation. John is a council member and past chairman of the Ground Source Heat Pump Association and has had a major role in the development of ground source heating and cooling in the UK. Dr. Anna Hitchmo has over 25 years working within the geosciences sector as a hydrogeologist focusing on water resources, ground source heating and cooling, and contaminated land. Anna provides guest lectures at the University of Birmingham. She brings her extensive knowledge to guiding clients through the process of ground source heat and cooling, including regulatory compliance, such as applying for licenses and permits for groundwater abstraction and discharge and environmental assessment. I'll hand over now to Anna to guide us through how ground source heat can assist in decarbonising your project or development. Thank you, Anna.
Thank you, Hugh. So we're going to split our presentation into two parts today. I'm going to have a talk through to give an introduction for what ground source heat pumps are, the context in which they're used for, and the difference between different types, such as open loop and closed loop. And then I'm going to pass it to my colleague, John, who's going to talk you through a recent case study to show you how we put everything into practice. So the government legally bound themselves to achieve net zero by 2050. And there's a trend towards the use of renewable energy in the UK. And in fact, there's been an increase in terms of electricity generation from renewable sources from 22% in 2010 to around 60% in 2020. Now, heat is one of the UK's contributors to carbon emissions, and so ground source heat pumps are a very exciting potential part of the roadmap to achieving decarbonisation for the country and for individual projects that you might be involved in. As technology improves, heat pumps are becoming ever more efficient, and so their carbon savings are becoming more and more beneficial. At the current carbon intensity, a ground source heat pump emits around 70% less carbon than an equivalent gas boiler. And the figure here on the right illustrates the potential quite nice. So, we've got the cumulative millions of global heat pump installations on one axis and time on the other. Carry on with the same trend as now, we find that we're going to end up with quite a gap between the carbon savings we could achieve if we went for carbon zero. And you can see here on the top line this increased gradient, and there's a huge amount of decarbonisation there achieved through the use of heat in our projects. So how do they work? So they take thermal energy that's in the groundwater, or in fact water in a river or a lake, and it's mostly heat from the sun that's recharged every year during the hotter months. And we take heat from these sources, normally only about 5 to 7 degrees, so not very much, but then it gets amplified via an electronically powered heat pump ready for us to use. So that heat is then taken into hot water, and that hot water can be passed around a building and used for space heating through, for instance, through radiators. And it can also provide hot water for use in washing and be used in that way. An interesting feature of ground source heat pumps is that they can provide heating and cooling within the same system. So as potentially summers get warmer, if you've got a ground source heat pump in place, you might not need air conditioning as well in order to keep the comfort levels for your buildings. Now, ground source heat pumps are more expensive to install than a conventional fossil fuel system, but they are cheaper to run than oil, and they're a similar cost to gas. So here's a little diagram just illustrating how they work. It's a similar technology to a domestic refrigerator. If you ever put your hand on the back of a fridge, you might find that it's a bit warm, and that's because the pump in the fridge extracts the heat from the air and isolates it. So what we do in ground source heat pump is we take that heat that you can get out and then use it to heat some hot water. So it does need a bit of power to run, mainly for the use of electricity. And the efficiency of the heat pump is called its coefficient of performance, or COP. So that's the ratio between the heating achieved and the power that's taken to run it in the first place. But they produce a lot more heat than they take energy from electricity. So in this example, there's a coefficient of performance of 4. So for each unit of energy taken from, for instance, national grid or a solar panel, for instance, then on this you get 73 units of heat from the ground. It gets passed through the evaporating condenser to heat up some water sufficiently to heat up the building. So the main types and how they're regulated. So we have what's called an open loop system, such as this picture here on the top left, where water is taken from an aquifer and then the heat's extracted by the pump, and then you have the water which you take back either to the aquifer or to another. You can use it, put it back into a river or wherever you want. But this requires quite a lengthy process of licensing for abstraction and re-injection from the Environment Agency. At the moment, because they're working on streamlining the permitting process. Another type is a water source, where you have, this could be, as I mentioned, a large lake or a river, or even in some cases a canal. You can either have a closed loop or an open loop, so you can abstract water in the same way as the example previously, or you can put a closed loop of fluid which encourages the extraction of heat from the water through to the heat pump. If you do open loop, it attracts the same regulation as it would for the borehole, the open loop borehole system. For the closed loop examples here, you normally need quite a few more boreholes, and you would circulate fluid through the pipes in the boreholes and then encourage the heat to the heat pump and extract it in a similar way. So this example here are vertical boreholes, and you can also have horizontal schemes such as this bottom right example. You need quite a lot of land for that to get the same amount of heat. Until quite recently, closed loop systems weren't regulated very, very rigorously, but for about the last year and a half-ish, they've been taken into the environmental permitting regulations, and so now there's some binding rules. So unless you're close to a very environmentally sensitive site, you don't even have to tell the Environment Agency, but you do have to start putting some provisions in place if you are in an environmentally sensitive area. So if we have a closer look at an open loop scheme, so in this situation, we've got a series of lithologies of rock types, and we've got an aquifer down here at the bottom. So some boreholes have been drilled into it, a doublet in this case, which takes what's called here warm groundwater, although in the UK, we're probably talking about 11 to 14 degrees of water. That's taken up the borehole into the building, passed through the heat pump, and then the cooler water, with about, as I said, about maybe 5-7 degrees of cooler, and gets injected back into the aquifer at a suitable distance away, and then once it's down in the water, it recharges because it's taking the solar heat from the sun. If you re-inject it, such as shown in this way, that's what's called a non-consumptive scheme, and that's quite relatively easy. The Environment Agency will accept that in most situations because you're not taking groundwater from the aquifers. But if you use it in a consumptive manner, such as you can take the water out in theory, and then you could use the water for drinking water if you had an isolated building, that's a little bit more difficult if you're in a part of the country where there's not much groundwater available. One thing to think about with open loop schemes is you have to be very careful not to cause thermal interference between your abstraction and reinjection boreholes. So you have to space them properly. So I'll talk a bit more about that in the next slide. So if we have a look here at this picture, this schematic, you can see that in this borehole here with the blue dots where we're extracting water, there's a bit of a depression in the groundwater. And when you re-inject it here, there's a bit of a rise. So there's a mounding effect. So this can cause a local change in groundwater flow direction. So it might, because water flows to a lower potential, so you might kind of cause a backup of groundwater flow. So the way to stop that is you can space your boreholes far enough apart. There's no, according to your pump rate, there's no interference between them. You can also take advantage of the natural groundwater gradient. So in this example here, if you're in the mode where you're trying to heat this building, so you're taking water from this direction, if the groundwater flow direction is here towards the left, if you re-inject the cooler water, it will move away. So there's less chance of thermal interference and a backup of the cold water towards the warm abstraction point. The other thing you can do to make it really efficient is if you have a good balance of heating and cooling, because you can run them both at the same time, or even seasonally run it in one direction or the other, then the spacing, you find that the spacing can be much less, so you can fit more in and it increases the overall efficiency of the whole system. Here's a few pictures to give you an idea of the scale of the operation. So we normally are only putting a handful in for an open loop, but it's quite a big rig. You have a look here, it's the same rigs that would be used for drilling a water supply borehole. And the boreholes are really quite large. So for instance, you might be about 600 millimeters wide, so like 60 centimeters. This gives you an idea of what it looks like. So moving on to closed loop schemes, again, we're taking solar energy from the near surface. In this case, we're not as interested in whether there's an aquifer beneath the site. If you do have water in the rock, moving through the rock, even better, because it will recharge the ground more readily. But it can be in dry rock. The heat pump here is working in the same way. It doesn't matter to the heat pump whether it's coming from an open loop or a closed loop scheme at all, but it takes the heat from the same way. In this case, instead of taking it directly from the water, we've got this closed loop. So we have a fluid within the pipe, which has properties which allow it to encourage it to absorb heat, and it brings the heat up to the heat pump where it's extracted, and then the cooler fluid goes back down into the ground and then gets recharged again from the sun's energy. So here we have a picture of a closed loop borehole, a vertical one. These boreholes are much more rough and ready. This one's only, it can only be 150 millimeters diameter-ish, typically. They're normally about 5 to 15 meters apart. But you do need more of them to get the same amount of heat out. So as it says here at the bottom, you might have hundreds of boreholes instead of just a doublet or a couple of doublets for an open loop scheme. The pipe that we run through it, normally made of polyethylene pipe, and we make sure that we fusion weld them carefully so that there's no spillage of any of the fluid within them. Typically you would install them at depths of up to 250 meters, but you can get them now deeper ones which may go up to over 500 meters deep. It's good practice. There's a number of good practice documents available, and one of them would be to make sure that you grout all the way up the borehole, especially if there's any contamination at your site, and that will both prevent a pathway, preferential pathway of contaminant getting down into any aquifer or groundwater. And it also helps to provide a better contact between the ground and the fluid in the pipe, because we're trying to encourage as much heat flow as possible between the two. This picture here shows a straight U bend. Remember, it's got a little, there's a U at the bottom, remember, but you can get concentric boreholes as well. It all depends how much heat you're trying to get out and how efficient your particular geology is at transmitting and holding heat. Geology is really very important, in fact, because it impacts how deep you need to drill to get enough heat. It also impacts the spacing between them, the drilling method you want to use and how much it's going to cost, as well as the thermal performance. And it also helps to gather, if you have a geological survey before, it helps to identify any geological hazards such as artesian flow, which make drilling very difficult, or also any areas where you expect the borehole might collapse because of the nature of the rock. So because you need so many boreholes compared to an open loop, you've got to be really very fast, efficient, and it's got to be really well planned. So you would typically you'd try and drill 1 borehole a day on a large project. So the other option is horizontal loop, which I've talked about previously. So these are really shallow, typically about 1 to 2 meters deep and about 1 meter wide. Usually you excavate a series of trenches, though you can excavate the whole ground and lay a load of pipes there. There's various pipe junctures to suit this space in your application. So if you've got the space, these can be quite a cheaper, better option. And you can cover the ground afterwards in have a garden or a sports pitch or even a football pitch or a car park. So it's quite versatile in that way. Now, we've talked about ground source heat pumps being brilliant in terms of carbon reduction, but they also start to come into their own when you scale them up to a district scheme, and then they start to become financially very attractive as well. So they work in a similar way to a gas network or an electricity network, where several buildings share the same supply. There's 2 main, you can use open or closed loop, it doesn't matter. Just depends on the geology, which one's the most efficient in that area. And you can either have a low temperature scheme where the heat arrives at ambient temperatures, and then each building has its own heat pump to control its own heat supply. Or you can have heat temperature district schemes, such as the that John's going to go through in a minute, and also a lot of places like with an estate like a university or a hospital. Well, this will be their favourite scheme, where the heat is taken to the heat pump, controlled from there, and then distributed between the buildings in that way. Another really interesting application is a aquifer thermal energy storage scheme. In this particular case, this is for an open loop scheme. There is a similar scheme for closed loop, it's called something slightly different. But this can be really great if you've got the right hydrogeological conditions, because which would be, for instance, a quite flat groundwater gradient with little, with slow flow and so slow transference of heat between the abstraction and the injection borehole. Several of these in the UK now as well, for example, in London and Manchester, which are working really quite nicely. And these can be very, very efficient because you deliberately cause an area of heat in one part of the aquifer and an area of coolth in the other part of the aquifer. And over time, the heat or the coolth in those areas intensifies, making it more efficient. So in the summer, for instance, you could take water from the cold part of the aquifer, run it through the system, extract the heat, and inject that back into the aquifer. And then the next winter, because you've encouraged extra heat into it, you've got the background heat plus the extra heat from the summer. So now you can take the heat back out again, circulate it through the building in the other direction, and dispose of the waste coolth back over here in this part. So I'm going to pass over now to my colleague John, who's going to run through a recent case study that we've completed.
Good afternoon, everybody. Yes, I'm going to talk to you about an open loop project which we have very recently completed for Berkeley Homes at what is now called Lombard Square. So that's one of their artists' impressions of the housing scheme. So Anna, if you could go on to the next slide. The project scope, we were asked by Berkeley Homes and Enacret for our input to a potential ground source system for a planned housing scheme. At the time that we were called in, it was an empty site, 18 acres. The site had previously been used for several uses. It was actually Arsenal Football Club's ground back in the 1800s. and then various other industrial uses from 1950 up until about 10 years ago. So it was an empty site, but it is now a very large new housing development, Lombard Square, just over 1,900 new homes and commercial spaces. So the client wanted to reduce their carbon impact. This is the first time they tried something, the ground source system on a scheme of this size. And they wanted to do it via a district heating scheme. So Anna showed you a couple of options, an ambient loop or a central plant. They have their plan was to use a central heating plant for this one. So there's a large plant room with heat pumps in, distributing heat around housing development. Before any of this happened, we had to then do a site-specific assessment of the geology, hydrogeology of the site to see which type of ground source system would be best suited for this location. We considered closed-loop boreholes. They would have been viable, but because of the size of the scheme, they wanted something like 1.5 megawatts peak heating out of a total of about 4 megawatts. There would have been just too many closed-loop boreholes required on a very busy development site. So closed-loop wasn't really viable. So we then concentrated our efforts on open-loop. For heating only. There is a small cooling requirement on the site, not very much, but the ground source system only meets the heating requirement. It could do the cooling as well. So our hydrogeology assessment concluded that the ground beneath the site was very well suited for an open loop system. And we recommended that the first 2 boreholes of the system be drilled and tested, so that using the results of those first 2 test boreholes, we could then model how many more boreholes might be required to meet the 80% of the base load heat energy that they wanted from ground source. The remainder of heating, if the ground source can't meet all of it, is to be met by air source, and as another backup, there is a small amount of gas-fueled conventional heat. Next slide, please. So part of our hydrogeology assessment, we looked regionally. So that's that green, amber, red plot there is a large chunk of East London, just south of the river. You can see the river meanders at the top there. So the site is actually in the amber area. So we sort of modelled that our site was amber because it was just above a very favourable aquifer, i.e. the chalk aquifer, but the groundwater was very near surface. So that can, in some circumstances, make re-injection of water very difficult or not possible, because as you re-inject, the water level rises in the aquifer around the borehole or boreholes and can rise to and above surface. That's not something you want, but in this case, as I'll show in a minute, we were able to manage that issue. There was known contamination in some parts of the site, and so the design of our boreholes and the construction of our boreholes was such to minimise any movement of that contamination, and the boreholes, the casing design means that contamination, any contamination found during drilling, was removed and sent to a licensed receiver. There was also a small business just to the side of the site, bottling water in East London. Quite unusual, but we took steps to protect their business. Next slide. So from the site investigation on many old boreholes in the area, we established the underlying geology. That's a look at the local lithology there. So it was made ground right across the site, and then absolutely vital for this system, part of the alluvial deposits are a very sticky, dark clay and silt bands all across the site. Beneath that, there was some river terraced deposits, fairly thin bit of the Thanet sandstone formation, and then into the chalk. So the entire chalk formation is beneath the site. Next slide. And that's just a part of our conceptual site model. There was perched water in parts of the alluvial deposits above the clay. The chalk rest water level actually lies very close to ground level, a metre or two beneath, changed slightly seasonally. We also put in two piezometers, two monitoring wells, one just above the clay and one just below the clay, so that we could monitor whether groundwater level, the chalk water level, was rising to or above the alluvial clay. Next slide. So our first phase was to drill two what I will call test boreholes, but they are of the same design as the permanent boreholes, because open loop boreholes are very large and very expensive to drill. So you don't want to be drilling boreholes which can't then be used as part of your final scheme. So we drilled one borehole to the south of the site, one to the north. The local groundwater gradient was moving to the north towards the River Thames, which was about half a kilometre north of the site. As I say, we've drilled two shallow piezometers to monitor groundwater movement. We refurbished the local bottled water borehole plant to make sure that they weren't impacted by abstraction or re-injection from the ground source scheme. The two boreholes were drilled to 135 metres. The final diameter down at 135 metres was 300 mil. We abstracted from the southern borehole, injected it into the northern borehole at a rate of 30 litres a second. That was the sustainable rate that we found. That just shows the drawdown plot on the right-hand side there. It was an excellent test, and it proved that one borehole pair will do about 30 litres a second, or possibly more. We used those results to model that we needed one further abstraction borehole and two more re-injection boreholes, because when we were injecting during the test, we needed a bit of additional pressure to push that water back into the borehole, about half a bar. So we modelled that the total of 5 boreholes were sufficient to meet the 1.5 megawatt peak heating requirement of the site. Next slide. So we had 2 boreholes. Those were drilled just before they started developing the site. The next 3 boreholes were then drilled as they were starting to develop the site, and that site became extremely busy, to say the least. The additional 3 boreholes were also drilled to a depth of 135 metres with steel grouted casing through the sediments above the chalk, and about 5 metres into the top of the chalk to seal off everything above. So we ended up with 5 boreholes, and then the formal, very detailed and lengthy test pumping exercise, pumping from the 2 abstraction boreholes into the 3 injection boreholes, was carried out in challenging circumstances, because the construction of 1900 apartments was in full flight, and we had quite limited capacity to discharge into the sewer during the testing. But anyway, the final injection test pumping exercise proved highly successful, and we showed that the 60 litres a second that we required for the 1.5 megawatt peak heating was a sustainable rate of pumping and re-injection, and that the water quality was excellent. Well, it should be, because they're bottling it right next door. But water quality is a very, very important aspect of any open loop system. If you have high iron or manganese or 1-2 other minerals within the water, it can cause problems. That wasn't present here. So during the test, we were pumping at 60 litres a second, re-injecting all of that back to the 3 injection boreholes with a bit of overpressure of about half a bar. No movement of the groundwater was detected within the 2 monitoring wells, so that groundwater level is all completely contained beneath the clay layer. There was no bad impact on the neighbouring borehole. And using the results of the test pumping, hydrogeological analysis and modelling, we completed the Environment Agency abstraction licence application. and the permit to re-inject water back into the 3 injection boreholes. And after about 4 or 5 months, the abstraction license was finally issued, and the legal document was issued to our client in November last year. Next slide, please. So in conclusion, this is an excellent system. The performance of the system is great. It's able to provide the full peak that they wanted of 1.5 megawatts. The presence of that superficial clay layer was vital to this particular application. Also, the presence of known soil contamination from previous industrial use wasn't an issue. That was managed by design and by borehole construction methods. The 5 boreholes were drilled, completed, tested, and all plumbed into the district heating system on a very busy construction site. Not easy, but it can be done. The system has now been adopted by Vital Energy on a 40-year energy services contract. That's the way a lot of these systems will go. But the client that is building the housing or whatever buildings that they are constructing, the energy, the heating, the cooling will be taken on, adopted by another company, and they will sell heat and cool over that period. The nearby water producer was protected, and their borehole is working fine. Because the groundwater quality is so good, we predict that there's going to be very little long-term maintenance required from these boreholes. There will be some. The ground source system provides a very significant reduction in lifetime carbon emissions, something like 24,000 tonnes in the first 25 years of operation. But this open loop system has been adopted for 40 years and may well operate for a lot longer than that. And will also provide protection against gas price and availability. Who knows what the situation will be in 25 or even 40 years time. So this technology, whether it's open loop or closed loop boreholes, is widely applicable, whether it's a new build system like this one or retrofit. It's equally applicable. It's just a matter of design, a matter of assessing the geology and hydrogeology. And so it's absolutely vital to obtain the correct level of advice from the right people, geologists, hydrogeologists, at a very early stage to choose the correct site-specific method for accessing ground source heat energy. So open loop, closed loop. Get the right people in right at the beginning. We can then establish whether closed loop boreholes or open loop boreholes or a river or an estuary are the right methods for accessing renewable ground source heating. Okay, so that concludes a quick run through of our case study.
Thank you, John, and thank you, Anna, for that presentation. Very, very interesting. We've got a few questions that are coming through the portal now. So I think we'll start off with in the closed loop system, do you find you get heat transfer between the 2 pipes that are obviously within that borehole?
Well, there is a degree of interconnection, thermal interconnection between the 2 pipes, but that's all taken into account as part of the design. So with any substantial closed loop system, you model the system knowing the properties of the plastic pipe and the properties of the surrounding geology to compute how many boreholes you're going to need. You then drill 1 or more test boreholes and you thermally test that system so that you can find out exactly how much heat can be sustainably extracted or injected. And so it's all part of the design process. So that borehole is a system, whether there's transfer between one leg of the pipe and the other, that is all calculated, modelled, and part of the design process.
Right. Okay. Fantastic. I think this refers back to one of the slides you went through. Can you store energy within a a low permeability aquifer rather than the low gradient, higher permeability aquifer?
Yes, you can. I think Anna showed us a slide of an ATES system, an aquifer thermal energy storage system. That's where you're pumping water from in one direction in the winter and in the other direction in the summer, or it doesn't have to be seasonal, it's whatever the building requires. So you're building up, let's call it pools of warmed or cooled water within the aquifer. If you don't have an aquifer, then you can do the same with a closed loop array of boreholes. It might be in a 300 meters of thickness of clay. So you might have several hundred boreholes, closed loop boreholes drilled in that array. Part of that array, you build up a warmed area, and the other part of the array, you build up a cooled area and use it in a similar fashion.
Yeah, it's like John mentioned, if you get hydrogeologists and thermogeologists involved at the early stage, they can advise whether an open loop or a closed loop system is the best, because each site's slightly different, so we'll be able to make a recommendation on what the best solution is at that location.
Brilliant. Just a clarification, I think, from one of your slides. It says what is the cost per kilowatt hour, but really, is it cheaper to do the ground source heat pump than using gas? I think you covered that, but whether you want to clarify that.
Yeah, it's at the moment, with the way oil prices are, gas prices are, ground source heating, yes, it is a good bit cheaper than oil boilers. It is a bit cheaper than for a large system than using mains gas. The issue that we have in this country at the moment is that electricity is 3 times more expensive than gas, and heat pumps are 3 or more times more efficient than a fossil fuel boiler. So other countries don't have this issue. The government are aware and are trying to do something about it over the longer term. It's called the spark gap, trying to close that gap between gas and electricity prices. As closer those become, the greater the contrast between the cost of running a heat pump and burning fossil fuels. Ideally in 10 years time, let's say, the price of electricity and gas will be much closer. Therefore, heat pumps will be much cheaper to operate and much better in terms of carbon emissions. Within 20 years, most heat pumps will be zero carbon machines because they'll be running on zero or very low carbon mains power.
Right. And if you tie it up with, as you said, solar or another renewable source on site, then obviously you're not drawing that power off the grid.
Yes.
Sorry, John. Okay.
Yeah, you would need a very large, for a 1.5 megawatt peak heating output, you would need a very large solar or wind input. And obviously, it may not be sunny or windy at the time you want it, but yes, other renewables on supplying that site will displace some of the power you are having to buy to run the heat pumps. But for a heating only system like this, we predict a coefficient of performance of something like 3.5. i.e. at least three and a half times more efficient than a fossil fuel boiler system. If this was a heating and cooling system, then it would be even more efficient than that. Your efficiencies would be 4, 5, more than that. A well-balanced heating and cooling system, the efficiencies are very high indeed.
Right. On that point, we've got a question. Where there's a mix of heating and cooling, such as in offices with server rooms, is it the net heating and cooling which is then managed through the ground source heat system? Yes, so we've mentioned that ground source has the great advantage of being able to heat and cool. You don't need additional plant. So a traditional plant room would have boilers and chillers. A heat pump, correctly specified heat pump, will heat and cool either at the same time or in different seasons. So the plant room will be designed
so that if a building has, let's say, a gymnasium and a server room as well as rooms which require heating, then that heating and cooling will be managed internally, and it's the net heating or cooling which is then taken from or put to the ground.
Right, okay. I think one last question, if that's okay. Would a heat pump connected with processed water abstraction work, where there's an existing abstraction for processed water? So this is where we talk about an open loop system, and you talked about either replenishing the aquifer or reusing the water elsewhere afterwards.
You can use it, but it becomes more complicated in terms of licensing. It depends where in the country you are and how much water is available. If there's spare water available, you're more likely to get a license to use it, to not re-inject it, and to use it for something else. You've worked on an example, haven't you, John, where somebody's taken some of the water and used it for a swimming pool and for use in a hotel?
Yes, absolutely. There are applications of abstracting the water for heating and cooling and using it for something else. So there is a consumptive element. And for processed water, then yes, if that water is going to be rejected, then why not take heat out of it or dump heat into it? At the end of the day, it all comes down to what's the flow rate of that processed water. How much heating, how much cooling can you generate from that flow rate? There's a fairly straightforward formula for computing what flow rate you need to meet a given heating or cooling load. Like we said, 60 litres a second at the Berkeley Homes example provides about 1.5 megawatts of peak heating.
Yeah, and in some cases, the processed water will be at a higher temperature than background anyway, and so you've got an advantage there of extra free heat available that you can use for something else.
Yeah, makes the system even more efficient.
Brilliant. Right, I think we'll end the questions there. And as I say, further questions will be answered once John and Anna have had a chance to review these. So thank you again to John and Anna. And our next Down to Earth talk will be on the Tuesday, the 8th of April. And we'll be looking at utility mapping and tracing within the built environment and the advantages of post-processing of data following on-site surveying. So please remember to complete the feedback following the presentation. Thank you for attending today, and we'll see you again in April. Thank you.